So,
Got 1 point.
yeah. I had worked on 3 space shuttle flights a while back, maybe about 10 years ago, and then done a number of different things. But I also work in the film industry, so and I've always loved astronomy. So.
Excellent. And Andrew's being modest. Andrew actually owns a video production company. So if you don't think you can make money doing what we do, there's evidence that it can be done. He does all kinds of cool documentaries all over the world. And he's kind of a world famous videography and video maker. So he's a cool guy. If you guys want to know anything about video production, he is the one to talk to. What? Yeah, I know it's working. You trying to tell me something? I'm going. Why are you making hand signals at me? Okay, anybody else? Anybody else? This is your first time here. Oh, over here. I'm sorry. Right there, right there. There she is. Okay.
Hi, I'm Heather. I just love astronomy. And I found you through Meetup.
Excellent. Heather that loves astronomy. Oh, there's one way over there. I love this, guys. This is good. See, we can get B running back and forth. I love it when you guys do this.
He enjoyed me doing that.
Hey, I'm Person. I met John in a parking lot, and he had a giant.
Go, John. John gets 1.
He had a giant telescope, and he was so sweet, and he let me look through his telescope, and so that's why I'm here today. It was really cool.
I know. We know. Yeah. Okay, good. Great. Thanks. Okay, John. John is sweet. I've never heard John described as sweet before. That's pretty good. Touchdown, John. All right. Anybody else? You want to admit that this is your first time here? Anybody else? Nobody else. Okay, good enough. And Trevor announced that the stream audio is working now. Thank you, Trevor. Woo, you got it figured out for us. Now those thousands of people that are online can hear us. We actually do have a very large online audience, so it's a good thing. Okay, here's our agenda for this evening. And there it is. You'll see it when it comes up. And if you are online and you want to ask questions, you can send a question to our email address, jscslive@gmail.com, or you can enter it in as a YouTube comment, and Trevor Quinn will be gathering up those questions and presenting them to our presenters here tonight. And if you have a question in the audience or a comment in the audience during any of our presentations, B, as you've seen, has the mic over here, and Trevor's got the mic over here. We appreciate if you guys would talk in the mic so that people online can hear your question or your comments as we're going along. So just kind of let them know that you want to say something, and they'll get a mic to you. Okay, now, so if you would like to be on the JSCAS email distribution, we have 2 email lists. One of them is for meetings only that Ron takes care of. I don't see, Ron's not here, right? Oh, there's Ron. Okay, Ron, there's Ron. Anyway, so Ron does the meetings only one, and you can send him an email to that address there, ronsterlicker@dmn3.com. If you'd like to get just meetings only, if you want to get all the emails, you can send it to David down here, starhopper457@gmail.com. And if you can't write that down quick enough or get a picture of it, I see Andrew's getting a picture of it. That's cool because he's a high-tech guy. He does on video production company. If you don't want to do that, out on the table, there's this tear-off tab piece of paper. You just rip one of those things off, and you can take that with you, and you can send these guys an email and get on our distribution. So if you have signed up in the past and are not getting our emails, try it again, because we're aware that some people have tried to get on the distribution and they're not. So there you go. All right, green button blues. If the door is locked when you're trying to go out, you got to push that green button to the right side of the door, and the door can't stay open for more than 20 seconds or else it'll make the alarm go off. So if you go out and the door was unlocked when we came in, but if you go out and the door is locked, that's the way to get out of the building. All right, reminder to our presenters. Okay, reminder to our presenters. These mics are wired out of phase. That's why that one's pointing over there and this one's pointing over here. If you cannot hear yourself in the system here, then it's not working. Don't try to talk into both of these mics at the same time because it won't work. They're out of phase and we get no audio. Please use the mouse pointer instead of the green pointer so that online folks can see it. And like I said, these folks will go around with microphones for questions. So first up tonight, we have our main speaker, Justin McCullum, the James Webb Space Telescope. What we know about the universe is wrong? I hope not. Maybe most of it. But first, before Justin comes up here, let me tell you a little bit about him. And I'm going to see if I can do this without my glasses. Okay, Justin J. McCollum is a graduate of the Portland State University with a BS and MS in physics, specializing in optical microscopy. He moved to Texas in January 2005 to work as the physics laboratory coordinator for the Department of Physics, where he currently resides in Beaumont, Texas. His achievements include developing the astronomy course in the Department of Physics and developing classes in orbital and celestial mechanics for the Department of Earth and Space Sciences at Lamar University. He has earned several awarded recognitions as the physics and astronomy educator for the Texas Governor's School for the College of Education and the Human Development at Lamar University from 2007 to 2021. He's a member of several astronomy clubs in the greater Houston area and is a former 15-year member of the Beaumont Asset Club. His service includes several officer positions amongst the clubs, including FBAC Vice President, Novice and General Meeting Program Director at HAS, and former webmaster for the NHAC Club. From time to time, publishing online reports on the current state of comets, and his friends and fellow astronomers refer to him as Professor Comet. He is a former employee of the Aerial Partners working on a USAF project with the aerospace giant Leidos as their orbital mechanics data specialist. He has an associate's certification in data science and is working on a PGP certification in AIML with the University of Texas at Austin through the Great Learning Platform. He works as a part-time senior education instructor at Space Center Houston, a senior volunteer at the Georgia Observatory, and a part-time volunteer with the Insperity Observatory in Humble, Texas. So join me in welcoming Justin McCollum.
So we have this ready to go. So let's see. Press. Now, there's been a lot on, there's that mysterious icon there. There's been a lot of reports in the news, a lot of incorrect news about, oh, the James Webb Space Telescope is showing data that maybe we were wrong about the Big Bang, that maybe we were wrong about the age of the universe, because there's been a lot of galaxies that have been imaged by the James Webb Space Telescope that look to be very well developed, whereas in old Hubble images, they look like primeval galaxies, and whether or not the cosmology is being turned upside down. Well, let's look at this. One of the things is there anything we need to change, particularly when it comes to the cosmological redshifting? And is anybody familiar with cosmological redshifting? So basically, you've got galaxies, we see them further and further from Earth. They move at faster and faster speeds because of the expansion of space-time, and the light coming from these stars is going to be shifted into the red light. So when you're looking at an active galactic nucleus, that is the active core of a galaxy that emits a lot of X-rays, that light gets shifted into the infrared, and a galaxy that looks 10 billion light years away, well, that is the light travel time, and the galaxy expansion of space, turns out the galaxy tends to be about 30 or 40 billion light years away. You've got a very big observable universe that is a lot larger than the value of the age of the universe itself. And there have been some incorrect articles out in the news media suggesting that, well, we look at towards the top end right here, we expect, if I see that right, where we've got the galaxies looking pretty old down here and they're more modern up here, that instead of these galaxies here, well, they're looking more really well developed, really spiral-shaped galaxies. And the idea is that, well, maybe the universe is 10 times older than what we think it is. It's not 13.8 billion years old. They think it's 138 billion years old. Well, no, it's just we have to modify our theories of galactic evolution. Galaxies are probably evolving a lot faster in a shorter period of time than in the old conventional sense. This was one of the first images taken of the James Webb Telescope. This is referred to as the first deep field image. You can see how a lot of the galaxies here, you've got the giant central elliptical galaxies, these big monsters that are over 1 trillion stars, and you've got the galaxies over here that are warped because of gravitational bending. And from that bending, we can sort of look at the distribution of the radiation, how that's being manipulated by dark matter. dark matter, the only thing dark matter can do is bend the path of light with its gravity. It can't absorb, it can't radiate light, it can't emit light, it can only bend the path of light. And the galaxies are forming a lot earlier than theorized. The idea is that it takes galaxies long periods of time, hundreds of millions, sometimes a couple billion years, to be fully formed into these spiral galaxies, or where the spiral galaxies merge into these giant elliptical galaxies. A lot of the images, particularly in here, that looked proto-galactic from a lot of the Hubble images, because of Hubble's limitations. Hubble is a 94-inch mirror, big enough to put into the, when it was sent into space with the space shuttle. So it's roughly about well, it's a 94-inch mirror. I forgot what it was in meters, but it's a lot bigger than the mirror that we have at the George Observatory. Whereas with the big Hubble, with the big James Webb Space Telescope, that is going to be a 21-foot diameter mirror. So it's 6.5 meters. So it's a significantly larger mirror than the Hubble telescope. So as galaxies that look proto-galactic in a Hubble image, because we have a bigger mirror, we can gather more light, we have more resolution, we see that the galaxies look more fully spiral shaped, more as we would expect to see a modern Milky Way-like galaxy, rather than the sort of the proto-galactic misshapen warped clouds, like looking at some primitive galaxy that formed just 100 million years after the Big Bang. Now, if we look at the upper image, this is sort of the old idea about galactic theory. If you have a very dense galaxy that has a lot of mass and it's not spinning very fast, it's going to quickly collapse down into what we call these giant elliptical galaxies. A lot of the dust is going to cause rapid star formation. You get your first couple of generations of stars, and that's it. And then afterwards, the elliptical galaxy over billions and billions of years, it's just going to become redder and redder and redder. Whereas in the bottom image there, you get a galaxy that starts out as just this big cloud of hydrogen and helium, maybe some lithium and beryllium formed in the early ages of the universe. It's not very dense. It collapses down into a spiral galaxy. Now, what we find is that some of the oldest galaxies that we find in these images are within about 600 or 700 million years after the Big Bang. In the case of a lot of the images coming from the James Webb Space Telescope, we're finding that instead of that long period where we get galaxies colliding, you can see down here in this lower right image where we have two spiral galaxies merging into elliptical galaxy, spirals merging with a lot of dwarf galaxies to create the big spiral galaxies. And one of the ideas of galactic evolution is that a whole bunch of dwarf galaxies merge together to form the bigger spiral galaxies. And that's a long process that sometimes could take a couple billion years. But if you look over here to the left, what we're finding is that a lot of these Hubble-like, a lot of these modern sort of Milky Way looking like spiral galaxies are forming pretty quickly within just a few hundred million years, within a fraction of the time that is expected over what we would expect to have twice as much time for the conventional theories, where galaxies tend to merge together. They tend to either merge and to form these elliptical galaxies, or we have dwarfs and the spirals creating the greater spirals, or here a slow process where not a lot of spinning, a lot of mass, and quickly collapses into these ellipticals, whereas we have very little mass, less mass, and a lot of spinning. It spins into the spiral galaxies, and the old assumption is it would take a very long period of time. Well, at times being almost cut in half, to where you have half the time where the galaxies are quickly forming into these nice spiral and barred spiral structures that we have here. So rethinking of galactic evolution. Well, we can see here, this is another image from the James Webb Telescope, and we can see that a lot of these galaxies are quickly forming spiral arms. They're going to be still small galaxies that are a fraction of the mass of the Milky Way. So over time, as they collect a lot of dwarf galaxies and they merge with the spiral galaxies to become larger spiral galaxies, we can see here that they're already forming spiral arms. They already have a central bulge. They're already having starburst regions. And so what we have here is, one issue is the formation of supermassive black holes. Supermassive black holes take time to get together. You're having a lot of stars merging in the center of the galaxy. They tend to be very, very massive. They blow apart. You have little black holes, stellar mass black holes equal to the mass of the sun, and they merge together. And over time, you end up having black holes on the scale of millions to billions of times the mass of the sun. And the idea is that it's a very long process, but it appears that the process is occurring in a much more rapid case. There's a supply chain problem. Where is the matter coming from? Because if you have these primeval galaxies that are very small, maybe a tenth the mass of the Milky Way, and they're huge supermassive black holes in a short period of time, while these galaxies have to somehow accumulate more mass, that is, basically rob stars from other galaxies, swallow up other dwarf galaxies in order for them to properly form into their spiral structures. And so where is that matter coming from? Where are all those stars coming from? Are there any dwarf galaxies nearby that we can't see in these images? So there's that supply chain issue. And it's possible that that the galactic bars within the bar spirals may be that solution. Maybe that somehow that as there's probably some matter out here that we can barely see that is slowly forming into stars. The stars make their way through the barred spirals, through the bar, because most galaxies are going to have a bar and a spiral around it rather than a conventional pinwheel structure. And that material migrates into the center of these galaxies and builds up the mass to form these supermassive black holes as sort of an anchor chain, for which it's sort of a gravitational anchor to build up those galaxies. And possibly a less turbulent universe. If it's a very young universe where material is basically spewing out after the period of inflation, turbulence means a lot of disruption, and that can inhibit galaxies forming into their fully developed shape, requiring a longer period of time to become fully developed spirals. So if these spiral galaxies and elliptical galaxies are forming in a very short period of time, it means there's less disruption in terms of movement of matter. There's less process. There's fewer processes that would inhibit star formation, and as a result, with less turbulence, less disruption in the early universe, it gives an opportunity for galaxies to grow pretty quickly. We look at the material transporting through those bars, and some of these guys barely see it, but they have a bar here, there's a bar here, and the material transporting through those bars are going to be anywhere from 10 to 100 times the amount of stars with respect to the rest of the galaxy being transported into that bars, so that it will actually build up around the core and build up the core of the galaxy. So the core of the galaxy gets built up, and you get the supermassive black holes forming, and from that, the spiral galaxy tends to form from that. And these are galaxies that we see with a redshift of around 1 to 2.3. So we're looking at galaxies that are going to be in excess of 5 billion light years from Earth, some cases up to 10 billion light years, because as you go from redshift to 1 to redshift to 3, you're getting into galaxies that are really at the edge of what we can observe within just a few hundred million, within just a billion years after the Big Bang. So we have Hubble images, and then we have James Webb images. So what looks like basically just protogalactic galaxies, just mounds of hydrogen and helium with just few patches of stars forming here and there. We're finding them to be a lot more developed and actually having structure of arms and populations of stars. Here is where we have the Hubble images at the top and the James Webb images at the bottom. You notice the difference between mirror sizes, between the 94-inch mirror of the Hubble telescope versus the 21-foot or the 6.5-meter diameter mirror of the James Webb Space Telescope. Here we look at this galaxy, and it almost looks like a protogalactic cloud. It just looks like it's barely forming. It looks like it's only forming a few patches. It doesn't appear to be having any spiral arms. But look down here when we have the James Webb image. Look at the difference. So we really have spiral arms. We really have a galactic core. We can even see star groups inside the spiral arms here. Look it up here. This image right here, we can see, and this is looking at 1 to 4 gigayears or 1 to 4 billion years after the Big Bang. We're looking at galaxies up to a redshift of 8. And here we can see that this looks like it would be almost like just a lump of dust and gas that's forming the first group of stars. But look down here. Look down here. Is it just me, or does that look like a nice spiral structure right there with spiral arms starting to form? So there may be some refinement of the dark matter model, and maybe that some of the effects of dark matter in a less turbulent universe is allowing there to be more organized dark matter halos that could contribute to rapidly forming these galactic structures a lot earlier, in some cases billions of years earlier than in the original theories of galactic evolution. If anything, it's probably causing us to modify our theories of galactic evolution rather than throwing things out. So what do we know, and does anything need to change? Well, what's interesting is that there's a paper that is out in the arXiv website, ARXIV, about, and this was found in a couple of news stories where they're looking at possible Milky Way size galaxies, about 100 billion solar masses in size. Galaxies are going to start out as a small size, and as they accumulate matter, right now we have about a dozen dwarf galaxies currently being consumed by the Milky Way. It's estimated the Milky Way has about 1 trillion times the mass of the sun. Of course, you have to take into account the mass of the dark matter halo. But this is looking at galaxies happening within just less than 1 billion years after the Big Bang. And some of these galaxies, we see a redshift of 7.4 to 9.1. You're seeing galaxies where the light took over 13 billion years to reach us, or around 13 billion years or to reach us. And so we see these galaxies. If we try to look at these galaxies today, the light would be completely redshifted out of the spectrum because these galaxies would be over 40 billion light years. What's interesting is that we don't expect these Milky Way-sized galaxies to occur very early within the first billion years after the Big Bang, because it's a long process of a galaxy that's 1/10 the mass of the Milky Way to really gather enough mass to really reach sort of up to 1 trillion solar masses, trillion times the mass of the sun. For those who are not familiar with that, that's 1,000 billion times the mass of the sun. Why do we say they're Milky Way sizes? Because these are comparable sizes to what we expect the Milky Way in its earlier ages when it was forming. And so if we think of every solar mass as being one star in these galaxies, that's assuming that's telling us that these galaxies already have billions and tens of billions, or at least billions and billions of stars already formed. And galaxies like these, we expect them to have significantly smaller number of stars forming over a longer period of time. When you look, if you ever go to the James Webb space site, the James Webb Telescope website, they actually have an area on their website, a link, a web page to the type of filters they use. So when they talk about F606 and F444, they're talking about filters on the scale of micrometers. And the James Webb Telescope can observe down to, I believe, 20 microns in microwave radiation. So it looks throughout not only in the near infrared, but also in the mid infrared. So we relate star formation with luminosity. One of the things is that the star formation rate is, we're getting the scale of the galaxies here are really on the scale of basically about 10 billion suns. So we look at redshifts anywhere from 1 to 3. We're looking at star formation rates that are significantly high. This formula here talks about how we take the infrared light and put it into a set of equations where we can shift it back into the ultraviolet. And this is at 2800 angstroms. So that basically is in the ultraviolet. And what we basically get is that's sort of a formula where we can look at the star formation rate. Basically means how many solar masses, how many suns, or how many stars equal to the mass of the sun are formed in these galaxies every year. And on the scale of the galaxies, we're looking at a lot of good star formation, particularly among galaxies that are having masses of over 10 billion suns and at redshifts of up to z equals 3. That's happening very early in the universe. Some of these galaxies here already have redshifts you can see of 12 and 13, and they're showing to have very high star formation rates, higher than expected in a universe that has to have less turbulence than what is predicted in a lot of the theories of cosmology and in early galactic evolution. Some of the earliest known galaxies, one of the things we look at is what we call the Lyman break, where after reaching a certain wavelength of radiation, basically everything is sort of absorbed by the dust. So that's what they call the Lyman break. Now, to the top here on the upper right, You can see where we go from a star to a galaxy far away. Any spectrum of a star, whether it's hydrogen or helium, is going to be shifted into the red. But how do we know then that that is the actual spectrum of the element? What's important is not only knowing the type of light, but in these lines here, the distances or the gap between the lines. That should be consistent when there's a difference in the position of one wavelength with respect to another. That doesn't change, but the wavelengths can shift. So if you know the gap between two wavelengths, even though it's shifting from the blue into the yellow here, we can still identify it as a particular element. And so we can identify that as hydrogen and put that into a formula and look at the distance of that galaxy. And I have it right here where we have this right here. This is one of my favorite images here. This is actually taken from old images from the Palomar telescope, the big 5-meter telescope in Southern California back in the 50s. You find this in a lot of astronomy textbooks. Here on the left, we go from a galaxy in Virgo to one in Hydra. So we have a distance of 78 million to nearly 4 billion light years. But look at the recessional speed, the speed at which the galaxy moves away from us, from 1,200 kilometers per second to 61,000 kilometers per second. And we can see the spectral lines here, which are calcium lines, shifting here from the visible into more of the longer wavelengths of light. So this is probably here probably in the blue light and shifting into the red light. Now we can look at the galaxies over here. We got these going from a redshift of 10 to a redshift of 13. And so we see the light being shifted in the Lyman break. And with the Lyman break, all the other higher wavelengths of light are going to be absorbed by the hydrogen in the galaxy itself, mostly just neutral hydrogen. And then the rest of it is probably just a lot of the dust spread out over billions of light years between us and that galaxy. Yeah.
Okay, so in the lower right-hand corner, you're telling us about this chart. I'm having trouble seeing the shift of the spectrum. Can you point out how, okay, where's that? Okay, where's that in the lowest one? Oh, it's way over there. Okay, I got it now. Okay, they all looked to me like they were all lined up. I didn't get it.
There's these two lines right here. It's hard to see, but this is the H.
Okay.
So as you have a greater redshift,
Okay, got it.
that's a principle of cosmology about cosmic expansion with redshifting. Yeah.
I understood that the end of the Dark Ages was 400 million years after the Big Bang. And you're talking about 325?
Talking about,
The end of the Dark Ages.
yes?
I understood it was 400 million years ago.
Yes.
But you have one here at 325.
So, I mean, it's what we have basically is probably have to have some refinement of, I mean, there was a Dark Ages, but it may be that the Dark Ages probably happened a lot sooner rather than a lot later. Because, I mean, it's unexpected. I mean, they're finding probably twice as many galaxies now, probably up to 200 billion. And they're finding these galaxies are forming into Milky Way structures a lot earlier than expected, more than half the amount of time. Now, this is where we're looking at the spectra of these galaxies. So up here we have this hydrogen and oxygen. You can see how it's shifted all the way over to here into the infrared. And we can see as we go from the galaxies of 11.3 to 13.1 billion years, that's the time which it took. When the news media talks about a galaxy that's 13.1 billion light years away, it's usually because that light began its journey 13.1 billion years ago. But when you take into account co-moving distance, because of the fact the universe expands faster than light, then the galaxy's distance is even greater. I mean, you're talking 25, 30, 40 billion light years. So galaxies move further away. They move at a faster speed. The light gets shifted longer wavelengths. That implies greater distances. But we're looking at galaxies that are actually forming at higher rates a lot earlier and are developing a lot quicker. So that means that in the beginning of the universe, there tended to be a lot of turbulence, a lot of disruption as the effects of inflation post-Big Bang. And when you have a lot of motion of material, it can inhibit the formation of galaxies. It turns out that that galaxies are able to form a lot quicker in a shorter period of time. That is, you cut the hundreds of millions of years to a much shorter number of hundreds of millions of years, 300 million versus that of 600 million. So that implies that in the early universe, there was less turbulence. So we see galaxy groups forming very, very quickly. So there's that red shift that we can see here. As we see the hydrogen, there's the oxygen, there's the hydrogen right there. And we can see as we shift into the infrared, we lose the hydrogen line right here, but we still have that hydrogen and oxygen over here. But instead of it being, let's say, over close towards, let's say, the blue part of the spectrum, it's now shifted into the mid-infrared. We also have new concepts in quasar astrophysics that may that are simply modifying or changing some of our ideas about how quasars are forming. Whether or not it overturns such concepts may be dependent upon new evidence. So is there any new discoveries that can contribute to new knowledge? Sure, as it overturns how quasars are forming, where you have a lot of material falling into the black hole. It has a disk of material that heats up and shoots out a lot of light. Here we can see the light at different wavelengths. You can see here, this is 700 kilometers per second. That's positive. So that's material moving away from us. We're over here, this is minus 350 kilometers per second. So that's material moving towards us. The green here is, believe it or not, a strong signature of ionized oxygen. We find that a lot of these are a lot of quasar activity. We're finding a lot of ionized oxygen. This really shows strong signatures, particularly if that material is remaining stationary, which means it moves out at right angles rather than moving away from us or towards us. And here we have some of this material actually moving away. So it gives us a depth of the material blowing out of the quasar towards us and away from us. As we look at different wavelengths of light, we're seeing the material move at different speeds. This is NGC 7469. You can see on the right, we have this invisible light. That's a Hubble image. Over here is the infrared. Look at the difference between the two images. We pierce deeply. We see a lot of gaps right here, as we can see where we have bubbles and cavities, where we're looking at new concepts. Well, we're looking at new approaches and perhaps having to modify some of our concepts of stellar formation as we get greater detail, piercing the depth of the dust lanes, where we can see a lot of these star groups forming where they really are masked by a lot of the dust lanes here. Now, opening the door to astronomy, this is Pandora's cluster. We can see some of the groups here. I actually picked out some groups here where we can actually look at galaxies actually forming. We have some of these nice spiral galaxies deep in the red color. If I pick out some galaxies from this square right here, so there it is up close. And look, I simply picked out a lot of the galaxies here. So it provides us new information. What we think are and you can see here, we got some dust lanes here in this galaxy. We got some spiral arms right here. This looks like a spiral galaxy forming. And this is really not quite pushing the limits of James Webb Space Telescope, but in Hubble, this would probably look nothing more than just a few pixels, like some sort of lumpy cloud of material just beginning to form stars. Now, the blue light shows the effects of light being bent around at high radiation light, high energy light by the dark matter. And over to the left is an image in visible light. So we can look at the visible light image here. And when we go back to the infrared, you see some of the lumps right here, which is actually galaxies being bent around as the light literally bends the light of the galaxy, so they look warped and distorted. It's much more magnified in the infrared, and we could somehow correlate that and compare that with the dark matter model that we're seeing, and it will help astronomers to modify any changes they need to theories of galactic evolution. This is a nice image right here. This comes from the JADES collaboration, looking at some very deep images. They did the same thing. They looked at an area of the sky that was even black to the Hubble telescope, even looking at hours of resolution. But look at the James Webb. Look at that. So we think that we've seen lots of galaxies with Hubble. Every one of those dots is a galaxy, with the exception of one star, or maybe two. That's it. And if you really pierce out, because I looked at the TIFF file for this, and it's like nearly a gigabyte. So you look deeper and deeper and deeper, you're finding galaxies that you can only see when you inflate this image by a factor of 100. So we start off with probably about two of them are going to be dwarfs. Before James Webb, it was estimated to be about 100 billion galaxies. Now we're looking at probably numbers greater than 200 billion. And a lot of these galaxies are going to be very massive. They're going to be generating a lot of high X-ray output, a lot of X radiation, but it's shifted into the mid-infrared. Particularly a lot of the redder galaxies in this image are up to a redshift of 12. Now, I remember with Hubble, it was a miracle to see galaxies around redshift of 3 and doubling that. So it's really looking within just the first 500 million years after the Big Bang. So here we pierce deeper into the images. We find a lot of galaxies not only rapidly forming, but I take one of the images from the JADE survey, I've blown it up, and you can see how we're getting that are forming very rapidly, but also we see a rapid development in the clustering and grouping of galaxies. So we see a couple of groups here that look like Higgson-like groups. You've got the Higgson group of galaxies where you get like just a few galaxies grouping together, but also we see a rapid process of where galaxies are starting to cluster very early. And clustering takes a long time because you get the groupings of galaxies after they form, the clustering and the superclustering, which allegedly would take about a few billion years, but this is, again, happening in a much shorter period of time. And then we get the sort of the red shifting as we see here. We got formation occurring within 2% of the age. We have redshifts of between 10 and 13. The critical wavelength cutoff is the Lyman break. And the Lyman break is important because where we have that break to where the hydrogen in the galaxy is starting to absorb the higher wavelengths of light, that will tell us a bit about where we are in that process of galactic formation in terms of the axis of the light that we can acquire when looking at these galaxies far away. But we really are looking at galaxies within 2% of the current age. We look at the cutoff emission, and that can tell us about the composition of these galaxies, the range of wavelengths being emitted by the galaxy when it starts off, when that light leaves that galaxy, travels through the universe, and where it shifts into that infrared. Now, the Lyman break, what do we mean by the Lyman break? Well, believe it or not, down here, this is the famous spectra for some of you college students taking physics classes. This is the Balmer series. So we got hydrogen alpha, hydrogen beta, hydrogen gamma, hydrogen delta. So this is sort of the specific spectrum, the emission spectra, for when basically you get photons being absorbed by a hydrogen atom and emits, and those light, they jump up into these higher orbits. So I have an electron down here. It absorbs a photon with a lot of energy, and it jumps up to here into this outer orbit. And then when it emits a photon around 410 nanometers of wavelength. So that's getting to pretty blue light. So that would be down here. And as we get down to 656 nanometers, for those of you who have a red laser pointer, that's around that wavelength. Now the Lyman series is right here. So notice the numbers are a lot shorter. That's going to be in the ultraviolet. So there's not only just an emission spectra, the famous Balmer series, and this is taking hydrogen light, putting it through a prism and splitting the light up so we can see the visible light itself. But up here we have a discrete spectrum for the Lyman series. And that's going to be the emission spectra in ultraviolet. And then the Paschen series is down here for the infrared. So there's a Lyman alpha, beta, gamma, delta, and epsilon. Here there's a Lyman alpha, beta, and the gamma. Where we place that limit there is around 912 angstroms, or 91.2 nanometers. Beyond that, the electron will simply just escape from the atom entirely. You end up ionizing the hydrogen gas. So this is for neutral hydrogen. So there's a lot of dust between Earth and the faraway galaxy. We got lots of dust within the galaxy itself. And the hydrogen gas by itself can absorb light beyond that set of discrete wavelengths. So we get that cutoff right here. And that cutoff can tell us a lot about the type of light being emitted by the amount of hydrogen in that galaxy, and tells us a bit about the amount of raw material for star formation. Now, beyond that, they fall between the U and B photometric bands. So if we look at the U and B photometric bands, this is what we call U-band dropout, where basically there's a dropout for a certain range of wavelengths where we cannot see these galaxies. Because if you look over here, this is in the far ultraviolet, we see the galaxy is invisible. It's cut off by the dust, by the hydrogen gas. But as we go down here, as we go from the near ultraviolet to the infrared, the galaxy becomes more and more and more visible. And that's the thing about the Lyman break. And that's sort of the bandwidths between the ultraviolet, the blue, and the violet for the wavelength in nanometers. We're going from 300 to 700 nanometers. So we're going from the violet into the infrared. So we get the cutoff at the U and the B. So we have to go down here into the violet because particularly with galaxies that are far away, it's best to see them in the infrared because we try to see them in the ultraviolet. We get into that Lyman break and the dust and the hydrogen gas is going to cut off, particularly if we want that hydrogen gas to remain neutral and not become ionized. Now, a lot of the galaxies have been referred to as these Lyman alpha emitters or these blobs. So they can emit that Lyman hydrogen alpha radiation as neutral hydrogen, so it doesn't become ionized, it doesn't lose its electron. But again, the limit is about 91, it's about 91.2 nanometers. Beyond that, the hydrogen starts losing electrons and becomes ionized. The emission here is around 121, about 1215 angstrom, so that's in the ultraviolet. The interstellar, when hydrogen is interstellar, you get energized, you end up having a high rate of starbursting taking place. And there's not much known about these particular objects. Here's this lump right here. This is an actual image of this blob of hydrogen gas that's really emitting a lot of the Lyman alpha radiation, and it's probably indicating a very high star formation. But you get very low mass galaxies that are very young, likely building up a whole lot of dust, and as a precursor leading to tremendous bursts in star formation taking place. I mean, 100 to 1,000 times the amount of stars that would form in the Milky Way right now. Gravitational lensing, this is a psychedelic search for the same galaxy. Well, believe it or not, this and this and this is actually the same galaxy. Why do we know that? Because the same absorption spectra and the same redshift value. That's the funny thing about galactic redshifting, particularly with gravitational redshifting, and of course with gravitational microlensing, is the way the galaxy's light is being bent around. So you've got a galaxy that's far away, you've got the galaxy nearby, the light from the galaxy is being bent by the gravity of the nearby galaxy, and if the galaxy is not lined up the right way, you end up getting 3 different images. Now, reason why these are in 3 different orientations is just how the light is, because remember, the foreground galaxy is moving. So as it moves, the field of gravity is changing by the movement of the galaxy, so it has an effect on how the light is being bent. So if you see these images year after year, you're going to see differences in how these galaxies are going to, the same galaxy is going to appear, and how it's sort of its companion here is being bent around, because these are a pair of galaxies here and here and here. The top image is a Hubble image. It looks very primeval, looks very young. But then again, we look at the same image again. It's about 600 light years wide. It's estimated to have about 1 billion solar masses. And we can look at you can look at the Lyman alpha radiation. And from that, there are equations when we look at luminosity with distance and mass and radius and the amount of area we cover when Hubble's away, and we get a size for that galaxy. So are there going to be new concepts that could add on to galactic evolution? Possibly, particularly if we're getting galaxies this small, accumulating a lot of mass and forming a lot of stars in a short period of time. So for gravitational lensing, this is interesting. This is a star called Lau 37, which is the source of the microlensing, as we can see here. So we have a white hot dwarf star. It's going to have a mass of about 56% the mass of the sun. It's providing some new insights. In fact, the microlensing, as it passes in front of a galaxy, we can actually get these stars to actually do gravitational microlensing. You can actually bend the light of the galaxies around it. So we're actually being able to study the structure of white dwarf stars with the James Webb telescope as the light of galaxies are being bent around it. So this is the first time that microlensing has been applied to measure the mass of the white dwarf star. It fits perfectly with a carbon-oxygen core, which means it came from a star a bit more massive than the sun, where some of the carbon actually fused to form oxygen. And so we talk about 56% the mass of our sun. We're talking about a star that, well, the white dwarf itself is going to be a bit bigger than the planet Earth. Here's some information about the movement of the stars in the constellation Musca, which is in the southern hemisphere. So it's something, unfortunately, we can't see here in Texas. You have to go south of the equator to see it. But it is only about 15.1 light years away. So that means it will actually move in front of a galaxy, then it will move to another part of the night sky and continue to move pretty quickly through the night sky, through the galaxy. This is actually, here's a good example. This is another image from the James Webb. You can actually see this galaxy right here. This is not a Hollywood image. This is actually a galaxy being warped around. So we can see the spiral arms here. We can see the core of the galaxy. So it looks like this is a nice spiral galaxy. And here we can see this process of where a foreground object acts as a lens, where the field of gravity bends the light from the source around the foreground object to reach the observer. So we see a galaxy over here. There's another galaxy in front of it. The gravity of this galaxy nearby bends the light of this galaxy, and we see it as this warped image on the other side. Also, sometimes most of the time, the gravitational microlensing acts as a magnifier. We can sometimes see these galaxies at 10 to 100 times their size. So they're magnified about 10 to 100 times. So we actually get to see this galaxy up close with detail, where it will look a bit fainter if we didn't have that galaxy in front of it. So the microlensing allows us to see these galaxies up close. So we get a little bit of help from Mother Nature. So we have the concept of gravitational microlensing. We get the galaxies passing around, the light from galaxies far away that is being bent around by the gravity of nearby galaxies, and they're getting magnified. So we get a bit of greater detail. That should be down here. That's 50 arc seconds from end to end. And that gives you the scale of what we're seeing here. And we can see the bending of these galaxies along the edges. And that's all due to microlensing. What we see is these light patches right here. Now, believe it or not, whereas these galaxies are not remaining stationary in this foreground cluster of galaxies. They're actually moving around. You don't really notice it, but if you were to look at the spectra of these galaxies, you can tell they actually are moving through the night sky. And they're moving around inside its own cluster. So we see these galaxies, we actually see these star groups. This is a galaxy where the light has been spread out from the microlensing, and we get a star group here, we get a star group here, we get a star group. So we can actually look at individual star groups, populations of stars within that galaxy. And as the foreground galaxies move around, these patches right here will actually appear and disappear and actually move around. The same way you can distort an image with a lens. As you shift the lens, these galaxies move around, the gravitational microlens is shifting around, and that shifting around can tell us much about the movement or the concentration and changes in the density of dark matter within this dark matter halo that surrounds this supermassive group of galaxies. So it's a way to improve the accuracy of determining the evolution of these galaxies, and also improve the methods for measuring the amount of dark matter. Now, the image to the left is Hubble. The image to the right is the James Webb Telescope. So that's the image from the James Webb Space Telescope on the right. There's Hubble on the left. It's that same group of galaxies, the first deep field image. You notice a big difference. You see a lot more galaxies. You see more detail in these microlens galaxies that almost look invisible in the Hubble image. So we're seeing new insights into the distribution of dark matter. We're seeing possible modifications to evolutions of galaxies and globular clusters, the formation of clustering, searching for the earliest stars, improving measurements of cosmic distances, and looking at changes to how we see what is the effect of turbulence in the early history of the universe. Now, believe it or not, is this an optical illusion? No, we're actually seeing the same galaxy. These are all the same galaxy right here. So as the way the space-time is being warped due to the gravitational microlensing, if the galaxy is not exactly behind the foreground galaxy, it's off to the side, we can actually see the galaxy being bent. And now up here, this is a different galaxy. This is a different galaxy. That's a different galaxy. But we see the same galaxy here, here, and here. And we can actually look at this right here. That is actually a supernova explosion taking place in a galaxy where the light took about 12 billion years to reach us. Now this is possible with microlensing because the galaxy is being magnified by the gravitational microlens. Otherwise, that galaxy would be hard to see without the microlensing. So the one thing about microlensing is that the gravity acts to enlarge the size of the galaxy. And being able to look at this supernova, we can use what's called the distance luminosity relationship and measure that galaxy's distance from the Earth and from the Milky Way without worrying about the effects of gravitational microlensing, worrying that that light is going to distort the shape and the appearance of the galaxy. Now, these images were taken over a period of about, you can see here, 320 and 1,000 days later. So there's that supernova and then it's gone. So shows you the consistency of supernova behavior. This is interesting. It's not possible to use Hubble to see the early ages of the universe. This is from a Hubble image showing what's known as the sparkler. Has anybody heard of the sparkler galaxy? We're going to talk a bit about the sparkler galaxy. We can see where here the Hubble, the resolution is limited. Look at all these individual dots right here. And this is a galaxy that's being redshifted. And the idea is that we're probably seeing globular clusters in a galaxy that is billions and billions, that took billions and billions of years for that light to reach us. So we're looking at a galaxy that's going to be 10 billion light years, 10 billion, well, where the light took more than 10 billion years to reach us. So we're looking at a galaxy that's going to be a couple dozen billion light years away by now. We can get views of globular clusters in galaxies far away like M87, but those are less than a billion light years from Earth, within a few hundred million light years. Now, oops, I went a bit further ahead here. So the red spots here are likely globular clusters. We can see some of the white patches, which show star formation regions, and these are both of the same galaxy. So we see the galaxy in different orientations, the way the light is being bent, because the field of gravity, because the galaxies are not all distributed uniformly in the supercluster. That's the foreground object, the object closest to us, the group of galaxies that are closest to us. It's going to cause the galaxies to be far away for their gravity to bend the light to where where we see the galaxy look differently in these three images. So in other words, it's not a perfect lens. It bends the light differently where we see that galaxy lined up with the foreground galaxy. So we have so basically what we see here is that we see three different versions of the same galaxy. We know the formation period within the first 500 million years. The cluster is over 13 billion years old. There are white dwarfs that have been detected at 12.5 billion years. The Z value, that's from looking at the spectra of these dots. The Z values are around 5 to 9. And that gives us a current distance of about 13.7 billion light years away. Now, I put in the circles right there. Those are going to be our globular clusters. The pink areas that we see numbered there are what we call quench systems, where when we're talking about quench systems, we're talking about how star is cut off instantly, where we have a certain amount of mass that forms a certain amount of stars, but given turbulence and radiation, the material is either is likely blown away, and the star formation process stops. It goes from a star formation rate of a certain number of solar masses to zero. And that's the quenching that takes place here, where the star formation process stops. The blue areas are where we see basically star forming regions within the galaxy itself, where we have the younger OB stellar groups, the younger stars being formed, versus the older globular clusters. So right here we can see the differences of the population 1 versus the population 2 stars, the older stars versus the younger stars. And it's right in this galaxy that's far, far away. There's about 12 of these that have been that are candidates for being globular clusters. So we get a lot of magnification. The masses of these globular clusters are fitting within a mass of around anywhere from 1 million to 10 million times the mass of the sun. So we're looking at the very massive globular clusters. There is some degree of absorption or light loss, probably due to maybe some nearby objects, nearby galaxies that are bending away the light, probably a lot of dust, and other stars that can sort of act as little micro lenses, and that can also affect the pathway of the light itself. And if there's any type of quenching taking place, that's going to interfere in the star forming place in this galaxy, where the star formation process is cut off. Yep.
Working? There it is. Okay, so that F090W, is that 0.9 microns? Is that what that filter is?
Mhm.
So that's just in the near infrared. It's just right outside visible, right? Okay, thanks.
And then you've got, that's my understanding with the James Webb, because what it is that the number here is a number that because Hubble can see the James Webb can see in the near infrared. And it goes as far as 20 microns. If you're not familiar with the population stars, well, there's two populations we know for certain. There's the population 1 that exists in the plane of the Milky Way. These are stars that are very young, they're hot, they're blue. Stars like the sun, which have metals, we have planets forming around them, particularly rocky planets, whereas the population 2 stars are here in the center or in the globular clusters. They're very old, they have very little metal. They likely will have gas giants forming around them, if that, and those are going to be the older, redder stars. But there's also the concept of population 3 stars. The difference between population 2 and the population 3 is that these are mostly stars that are balls of hydrogen and helium. They may have some lithium and beryllium, but that's it. No oxygen, no carbon. So you're talking extremely metal-poor stars with no planets. The mass range, I've seen most between 150 to 500 suns based on theories about population 3 stars, but I've seen some really wild theories of them being up to about 100,000 times the mass of the sun. But these are stars that would only live for about maybe 1 million years. And they all existed within the first 1 billion years. None have been found today in terms of the time within the first billion. Well, in our local area of the universe, we don't find any of them. Any surviving remnants are going to create very massive white stars, the massive N for neutron stars, and the intermediate mass black holes. Black holes that are tens of thousands of times the mass of the sun. Something that we would find maybe in the center of a dwarf galaxy remnant, like Omega Centauri is we classify as a globular cluster. They're going to be very hot. They're going to have very blue. They're actually at the very hot end of O-class stars, so surface temperatures of over 50,000 Kelvin. The sun is about 5,800 Kelvin. So we're looking at stars that have a surface temperature more than 9 times that of our sun. Very, very rare. Right now, there's no direct evidence for population 3 stars, but there's some potential candidates. There are some quasars. There's one quasar where they find a high abundance of iron around the quasar, likely as a result of a population 3 star going supernova. There is one star where they have found evidence of ionized oxygen and carbon in the star's spectra. And one thing is where we find the pristine cosmic material, because we would expect these population 3 stars to be everywhere, particularly around here, while the first stars are forming just 300 million years after the Big Bang. But it turns out that in the first 2 billion years, we find that there's just simply a few isolated locations of where there's pristine material, that is pure hydrogen and helium. So it may be that the population 3 stars only form in certain areas of the universe rather than being formed everywhere. This is such the method right here where if we look at stars that are metal poor, if the stars are going to have some amount of metals here, which is having a lot more iron compared to the hydrogen, These are the stars that are going to be very, very massive within the first billion years. So stars up to 280 times the mass of the sun. Whereas if we look at something with magnesium versus iron, we find that there's a lot less of the heavier metals and a lot more of the lighter metals. But these are stars that are going to be still pretty metal poor. And those are the type of, this is just a model. It's what we would expect to find when we're looking at the spectra of these population 3 stars. If we're going to find some metals, we expect to find some amount of iron, but very little magnesium, but the amount of metals are going to be extremely small compared to the population 2 stars. What we find is that there are some limitations with the James Webb Space Telescope, because to find these population 3 stars may be a bit beyond the James Webb Telescope. The redshift ranges are going to be high, the magnitude 40 to 45th magnitude, where I believe the James Webb is limited to about 29th magnitude. There's talk by some astronomers to create what they call the ultimately large telescope on the far side of the moon. That is building a 100-meter mirror. Because you're going to be searching for galactic halos of galaxies for masses of around probably 10 to the 7th, which is between 10 million to 100 billion solar masses. And what the graphs here show you is that it's very rare to find, compared to stellar mass and luminosity, it's anywhere from 1 out of every 10 to 1 out of every 100 million stars will be a population 3 stars compared to the population 2 stars. So that means the population 3 stars are going to be very, very rare to find. They're going to be very massive, they're going to be very bright, but it may be that we only find one of them for every 100 million of the old population 2 stars. So they're going to be probably very, very rare. This is sort of you can see here, that's the star that we're talking about. That's our candidate right there. This looks at the difference in terms of the brightness of the stars based on the amount of mass, in terms of the brightness, in terms of the mass, in terms of the red shifting. So basically what we're looking at is, I'm walking off. Over here on the left, this goes up to about 1 million times brighter than the sun. This goes to about 100,000 times the mass. And we can compare that with the population 2 stars, where we can when we're looking at the accumulated mass of all the population 3 stars in certain regions. Possible candidate for a population 3 star. The issue that we have is that we're finding a lot of the oxygen and carbon that's being detected. The area around the galaxy where it's formed has a star formation rate of 2 solar masses per year. Basically, this turns out not to be a good candidate for a population 3 star, as we thought it was. But I mean, it's technically, its magnitude in the ultraviolet is negative 19.58. So it's about 6.28 billion times brighter than the sun, ultraviolet-wise. I mean, we'll expect to find population 3 stars that are going to be billions of times brighter than the sun in the ultraviolet. But the one thing that's killing it is this O3 and this carbon in its spectra. We would expect population 3 stars with no oxygen or no carbon, mostly just hydrogen and helium. And this is what we're looking at here in the ultraviolet sea, right there. Because a lot of this is looking at the Lyman alpha that's in what we call the ultraviolet C type radiation right there, between 100 and 280 nanometers. So when we talk about the Lyman break, we're looking over here in the type C ultraviolet. Strong Lyman breaker right there, looking at the ultraviolet C, looking at the atomic hydrogen, because one of that's where we're looking at the candidate here and see where that population 3 star fits within based on its brightness, based on the mass, based on the spectra. But the one thing is that we're finding that the process of ionizing that radiation is in the reverse. Usually you have When you're ionizing hydrogen, photons get absorbed by the electrons get stimulated, and then they emit photons. Here we're finding that hydrogen is emitting both electrons and photons. And it's very bizarre because that's not what we would expect for a population 3 star at all. So they're likely out there. It's just that there's just what we think is a population 3 candidate. It's very difficult to look at a lot of these stars and call them population 3 stars when they have a little bit of a quirk in them that cancels them out as a candidate. So one thing about the James Webb Telescope is it can provide us opportunities to try to find actual population 3 stars versus sort of the phony population 3 stars trying to have some of those properties without them actually being population 3 stars. So we want to search only for pristine material, mostly hydrogen and helium, high radiation, intense UV light. There are what we call PIS-N signatures, which deals with pair instability supernovas. You've got what we call Wolf-Rayet stars, which are very bright blue supergiant stars that produce pairs of positrons and electrons. Positrons are positive charged electrons, sort of antimatter pairs just before they go into extreme supernova explosions. The absence of metal in a spectrum that should be uncontaminated, that is, doesn't have any spectra of any metals, maybe a bit of lithium. High. That means we're looking at these stars at the earliest ages of the universe, less than 500, 400 million years after the Big Bang. This is not an actual image of this galaxy, but this galaxy was believed to have been a candidate that contained population 3 stars, or as a possible location. This is an artist's impression. I've seen the original image when going to Sinbad. It's just a puny little fuzz spot. But the idea is that if James Webb were to look at this, maybe it could find some of those population 3 stars. The gas drag and dust segregation. The one thing about looking at this is finding the low counts of, see, a lot of these are just low numbers and negative numbers, so we don't expect a lot of nickel, we don't expect a lot of oxygen or magnesium or silicon compared to the amount of iron. We tend to find a lot less of those other metals comparison to iron. So there's a lot of dragging. There's the dust segregation where you actually separate out the very dense dust from the less dense dust. And there's a process where we have that we call this Coulomb drag, where basically electrical forces can actually impede the motion of this dust from escaping from the star itself. Whereas if the radiative force, if it goes beyond a value of 1 here, basically it can overcome the gravitational force of the star and dissipate into space. Or if it's below the value, you get this Coulomb drag where a buildup of voltage, of electrical energy in the accretion disk forming around this population 3 star can keep the material within the accretion disk and help it build up its mass. Green peas, this was actually very interesting. They go under high star formation rate. The average green pea is about 3,200 million years old. There's no galactic active nucleus, but there's a lot of high star formation. These are leakers of the Lyman C. So when we talk about the Lyman C, we talk about the ultraviolet C radiation, because beyond that, we don't see anything else because of the blockage. We don't see any of the shorter wavelengths of radiation because of the blockage from the hydrogen and the gas in these green peas. These were not known until the Galaxy Zoo project. I talked about the Zooniverse. It started off as the Galaxy Zoo project for citizen scientists. When this came out in July 2007, as the dawn of the Galaxy Zoo project, they were starting to find these green peas like crazy around the Milky Way and in galaxies within a few 100 million light years of Earth. Lots and lots of these green peas, these ultra compact dwarf galaxies. Well, now they're finding them in the James Webb Space Telescope. So we're finding these green peas that are very, very far away. And they're containing unusual concentrations of lithium beryllium, a lot more than we would expect. I mean, you get the hydrogen, you get the helium, and then the lithium and the beryllium are the next elements to form, but they're going to be in very, very tiny amounts using conventional theories of galactic evolution and early cosmology. Well, we find out that the concentrations are very high in these peas that are actually being seen in the first 5% of the age of the universe. And they still maintain the same absorption spectra as the green peas that we see nearby. Because of the strong peaks in the oxygen. And we see that with the green peas, regardless of whether the ones that we find in the galaxy zoo that are close to the Milky Way, relatively close, versus those that we see here at the very edge of the cosmos, which indicates there's a lot of metals being formed in these galaxies a lot earlier than expected. So this is the common spectra for the green peas. This is from the Cosmic Web Dawn project. This is from the Deep Sky Sloan survey. So these are looking at galaxies that are going to be about a tenth the distance from the Milky Way versus these which are going to be much further away. I mean, these green peas are within about a few hundred million light years. These are green peas that are seen within the first few hundred million years of the age of the universe. But look at the spectra, look at the peaks. The neon, helium, the oxygen, the mostly hydrogen, oxygen, and neon, but look at the peaks, they're exactly the same. Mostly the same, so we get the same spectra. So the spectra of the green peas are consistent regardless of where they are in the universe and regardless of where they are in the age post-Big Bang. Yeah. We have to be out here by 9:30. Okay, so more hidden galaxies, yes, more hidden galaxies, more discoveries. Particularly, we can see here in the Stevens Quintet. This is the Wolf-Lamarck-Lamette galaxy. And quasars, we're finding lots of very massive quasars, a lot of massive quasars that are a lot brighter. This is, I'm going to wrap this up here. This is the constellation Hercules. That's a Lyta galaxy. Look at that. Lots of galaxies now, and we can find very fully developed galaxies. Brown dwarfs, we actually found a brown dwarf with a sandy atmosphere, an atmosphere with a lot of silicon and sand. So there's the silicate cloud right there. And that's where we fall into the spectra itself. So, and where it is in terms of brightness and age. And this is actually looking behind NGC 346. This is NGC 7320 in Stevens Quintet. We got all the dust. This is the first time we ever looked at Stevens Quintet and actually find galaxies on the other side. So we get a lot in terms of the turbulence of star formation taking place. The depths, Stromgren spheres deals with the bubble of radiation forming around as the dust erodes from the radiation gas. And I had to wrap that up a bit, but are we overturning science? Not yet. So. Anybody got questions? Questions?
Yeah, Justin. Can you go back to your slide that you had the 6.28 billion time luminous in ultraviolet compared to our sun?
Let me go back.
Anyhow, my question is,
Yeah.
maybe I'm not understanding population 3 stars very well, but when you've got something that is that bright in ultraviolet, that indicates to me that it is a gigantic, massive star that is super hot.
Yes.
Okay. If it is massive and super hot, well, that holds with theory that stars that are big and hot burn hot. They
have a short lifespan.
Right. So, but in the process of having that short lifespan, they have oxygen and carbon get formed pretty rapidly in the cores, right?
Not as it's understanding with population 3 stars.
Then why is stellar dynamics different for population 3 versus current stars? I mean, it's still fusing the same way, right?
Well, the stellar dynamic theories apply up to the Eddington limit for about 150 solar masses. Beyond that, stars do some pretty strange things. radiation can overpower the gravitational field if the star reaches beyond a certain temperature. Of explosion, then you get a lot of those heavier.
Okay, thank you. That clarifies it. Thank you. Appreciate it.
Yeah. Okay. I'll let you.
All right, thank you, Justin, for that very interesting presentation, and we will be able to continue talking about all this at Mod Pizza after the meeting. Let me get to where we are here, boys and girls. Okay, sorry, guys, we have to be out of here by 9:30, so we gotta move on. Oh, while I'm doing this, Elisa? Yeah, so Lisa's our representing LPI tonight. She's here helping us out, so let's give her a hand. She could probably be doing something else that she'd rather do, but she's here taking care of us. Okay, oh, whoops, whoops, ah. Hold on. Okay, Ron, do you want to say anything about DVD library, yes or no? Make it.
I dropped it in the driveway. So, but it'll be here for the next meeting.
Okay,
Got a lot of, Infinity Cosmos is, astronomy magazine, the great courses. Anyways, it'll be set up at the next meeting. Thank you.
all right, thank you, Ron. Okay, so after the meeting after the meeting, we're gonna go to Mod Pizza. You come out here, Middlebrook, go north till you hit Clear Lake City Boulevard, then take a left on Clear Lake City Boulevard, past El Dorado, and right in front of the HEB, there's a Mod Pizza. We'll get together and we'll continue talking about astronomy and other things. Everyone's welcome to join us, especially all you new folks. Come on, you'll have a great time. It'll be fun. So please join us at that right after the meeting. Okay, we're gonna take a 10-minute break, and after the break, we will get back together and start the second half of our meeting. 10-minute break.
Balance.
Problem is, the threshold limit The convection zone, they have no radiator zone.
Okay, 45-second warning. Is our next speaker. 30-second warning. Okay, we're gonna start anyway. Wants to go eat pizza. Okay, so next up, we have our Vice President, Chris Wells, to catch a comet.
Okay, good afternoon. This is probably at the opposite end of the spectrum to what you just heard. This is the most amateur presentation you're ever going to get rather than the professional one that you've just heard. So to catch a comet, this is all about having some fun with your astronomy equipment. So there we go. Oh. How to do it. Okay, so to catch a comet. So every now and then you hear about a comet and you see these just incredible skyscape images of comets and their tails and their ion tails, and you see them in front of mountains and skyscape images. This is not one of those presentations at all, right? This is the reality of these visual eye comets and actually seeing them in our sky, on our sky pollution area. So, you know, we all live in this kind of area where it's sort of 4 to 8 scale sky pollution that really does play havoc on that experience that you really want to get when you see a comet. So this is a presentation about finding, imaging, and processing comets here from really Light Pollution Central. Okay, a couple of maps here. If you want to see how bad your viewing conditions are, there's the Clear Outside app. It tells you the Bortle scale that you're on. Also, how do you say that? Astroperic application. Look at that. Look how horrible that is for viewing. But it doesn't stop us trying, right? That's the whole point about this DIY presentation, is that if you hear about a comet and it's a fairly bright comet, go for it anyway. Go try and find it, whether visually or through taking pictures. Okay, so how to find them? Okay, simple. It's Sky Publishing always do these wonderful charts of where is the comet on what date. So you can actually see the dates in January where this comet came through, and this was during January and also December and January. So the first thing is to get a good sky map, and I always like just doing these online. Look at the Sky Publishing map, and it tells you roughly where this comet is. This was the path of comet ZTF, which is a circumpolar comet, they called it, C2022 E3. So this is its relative position. And then the first thing is then you roughly know where it is. You go outside, you look at whether or not you can even see that part of the sky. Is your tree in the way? Is your building in the way? That sort of thing. Or where do you need to use your legs to walk to actually go and find it? So that's in the planning phase. So do the planning, get the Sky Publishing map, and see where that comet is. Next thing to do is sometimes if you just want to do it visual, start off with a wide field telescope. So there's me outside with an old Astro scan. This was when I looked for Comet Leonard. Right, remember Comet Leonard around about, I think that was December 2021. Go out there with your silly hat on and just go and try and find it based on a sky map. Fun to do, and when you see it, it's pretty disappointing. Okay, because it's Light Pollution Central, it's just a fuzzy, and when you see that fuzzy, it's I don't know, it's just something fun about just finding things manually and say, hey, I got it. Come and have a look at this. Come outside, kids. Come and have a look at this. Oh, do I have to, Dad? You know, it's that sort of thing. But it's a great experience. It's fun to do. And it's different than doing what you normally do in Light Pollution Central. Light Pollution Central, what do you normally do? You look at the planets because they're really kind of cool to look at. You look at the brighter globular clusters. And all those showpiece objects are really fun. You go and look at open clusters like M35. Even if you want to be challenging, look for things like NGC 2158, its companion right next to it. So you get used to those showpiece objects that you look at. But the thing about comets is they come. They're different. They're interlopers through our solar system. So they're actually fun to go and find. And when they're gone, they're gone. So go and try and find them. It's a lot of fun visually. But it's also fun to go and sometimes capture that comet by taking some pictures as well. So how do I do that? I do it simply using Sky Safari on my phone. And it actually, I dial up the comet on my phone, and you look for its coordinates. It gives you the RA and the deck coordinates. Well, they keep changing, obviously, because it has its own relative motion. But at that point in time, take those coordinates, just type them into your go-to scope, and your go-to scope will then go and find it. That's how I go and find the comet if I'm interested in imaging. Now, you've got to also be reasonable about imaging a comet in Sky Pollution Central. It's not easy to do because after the tail and the ion tail as well. You're really after getting as much detail as you can when you're imaging, but it's right close to the sky pollution level. So you really got to try and separate it. So what you often do is take multiple images through your scope. So first of all, you find it using your go-to scope. And here's my go-to scope. It's just a simple Altaz mount. And I put on my small Sky 90 telescope. I've got there, that red light there is where a DLSR camera is stuck to the back of it. I use that go-to scope there, and then I try and keep it simple like that. And I use the just a remote bulb control on the telescope, on the camera, and then do 30-second images. That way, I don't have any computers. I just leave it running. So on this setup, I actually set this up with the camera. I'm imaging it. I've got a good focus. Use a double star. Use Bright's double stars to do good focusing. Get that, then go to your comet. Don't try and focus on the comet. You'll never do it. Not on a DLSR. It's really hard to do. So use a good bright double star, which is close by. Get your good focus, and then start doing your 30-second images. Why 30 seconds? Because often the DLSRs, certainly the ones I use, which are Canon, are limited to 30 seconds. But it doesn't matter when you're doing this. There's no guiding, there's just tracking. So keep taking 30-second images, which is fine on an Altaz mount. You can get away with that and start taking the pictures. And take as many as you can. Actually, I left this going for over 5 hours. And remember, the DLSR camera with the little battery in, it kept taking pictures for 5 hours. I was quite amazed with it because that camera's probably done about 1 million pictures. The same original battery still does about 5 hours worth of imaging, which I was absolutely surprised at. But anyway, so this is what I ended up getting. Okay, you do start to see the ion tail here. And there are two different pictures. I first of all stacked 85 images at 30 seconds. And this one's 199 images at 30 seconds. Obviously, the length of the star trails is about double between one picture to the other. But I was pleased to get ion tail there. Something you would never see in the eyepiece, not here in Light Pollution Central anyway. So it's fun to be able to do that. And the beauty of stacking is what you're trying to do there is separate the signal from the noise. The noise being the light pollution, you want to be above that. So the idea is to keep stacking it. The signal to noise of the image gets more and more enhanced. And that's the trick behind doing this. And anyway, so that's what I ended up taking. One for 85, one for 199. How did I process it? Okay, I was trying to keep it as simple as possible. I used a free application called Deep Sky Stacker. Actually, Doug, many, many years ago, introduced me to that. Thing about Deep Sky Stacker is you just load up the images. So I loaded up the 199 images. Okay, now what it normally does when it does stacking for images, it would actually align every image based on the stars and where all the stars are. And it makes a very good job of auto-aligning those. But Deep Sky Stacker doesn't know where the comet is. So you've got to tell it where every picture of the 199 images is actually placed. You got to, now, obviously doing that 199 times, because there's 199 30-second images, is a little painful on the carpal tunnel. Gets a bit iffy on that. So you don't do that. What Deep Sky Stacker has is the ability to select the very first image, the very last image, image number 1, image number 199, and also a registration image somewhere in the middle. And you just click on 3 images, and as long as the 199 images are sequential, and have a timestamp, a date timestamp on them, it interpolates all of them, knows exactly where the image is, and then can stack it for you. So no carpal tunnel, right? It does that for you, and it's really quite a powerful image processor to do that. And it gives you options to process it 3 different ways. Either you can do standard stacking, which means it will stack with the stars, and then the comet will be a big blur. You can stack on the comet, in which case the stars are going to be blurred, or you can stack on one, stack on the other, and it actually joins the 2 images together. Yeah, I've mostly had success with comet stacking. That one, I don't use this one that much. Anyway, so that's how I do the image processing. I then take it to Photoshop, just do a little bit of stretching, and you can bring out that ion tail in that way. And I've been doing this for a number of years since I got interested in comets. Here was Comet Leonard in December 2021. Here's another one, Neowise as well, in July 2020. Fun to do at home, use your equipment, take it out, have fun, come back and present to us your own images. That's what it's all about. Hope you enjoyed it.
All right, thank you, Chris. There's your vice president in his backyard with his telescope. Next up, Dave, Star Party News.
All right, I don't want to be between you and the pizza, so we're going to move through this. March 4th, week ago, tomorrow, we had an event at Magnolia Creek Golf Course. I'll talk about that in a little bit. March 16th through the 19th, I know Doug is going to be talking about this. The club's gathering at Fort McCavett. I'll be talking about Fort McCavett off the heels of this. 19th through the 22nd, X-Bar ran lapping a day. Some people are conveniently making a whole week, going from one to the other. April 1st, April 28th, we've got 2 tentative hack outreach events. May 14th through the 20th, take TSP, and then again, tentative events for hack. Clear Falls hasn't come back on the radar yet, Doug, so that's why I kind of put it there in the question mark. March 4th, Magnolia Creek worked out real well. I want to thank Chris Concert. Connie and I were there. Doug, Al Kelly showed up too, which was really fun to have him. Jody and Todd Zatorsky, Trevor and Mark DeCellis, and then Ron Ugaldi also showed up. At about 7 scopes, 75 in attendance. There's Trevor. There's Chris's monster. That's kind of the view we've got. That's what really why it works that way, because that's all the way from the east, although this isn't a panorama shot. East, south, west, there's not a lot there. The north is to our backs 90% of the time. So actually, this is kind of a fun place to be, and the lights on the horizon are fairly low. There's Al setting up his 9 1/4. I just dropped her name. She was parked right next to us, GEO. And then her husband's there, and then Mark's sitting right there. Most of these are in daylight, and the crowd just came down and just filtered their way through. Objects, M42, the moon. Al went crazy on stars as he usually does. So it was a good time for all. Yeah, he actually showed us 2 of the side stars that are in the trapezius of M42. It was pretty wild. Actually my scope, but Chris is conveniently posed right there. Thanks to everybody that came out. Yeah, it's strange, but I guarantee it'll come back. Australia enters the space race. All right, Fort McCavett. Some of you, this is really intended for the new folk. Also reminders for us old folk. Fort McCavett is still out there. It's a place we go to twice a year. And the spring trip coming up here is the 16th through the 19th, 2023. So I want to give you a little bit of details on that as a little bit of a primer. Where is Fort McCavett? About 360 miles, depending on how the crow flies. You come to San Antonio. It's a little bit. You can make it in a day. Kerrville is getting out there, and then somewhere up here, Junction. Once you get past Junction, there's not much there until you get to Fort Stockton. So if you start seeing signs for Fort Stockton, you went too far. There is a little side road over here. You turn around and you make that turn up. I said, keep going past Kerrville and Junction. FM 1674, take this on up, 23 miles. Basically, it's a marathon run if you want up hills and down dales. You do want to watch for deer and rabbits, especially at dusk throughout the evening. One time, Connie and I went and we counted 74 deer just going up. Half a dozen raccoons and a lot of other animals. You come up here, top of the road, you make the right turn, and then the fort is right here. Fort used to be a Texas State Park, but now it's part of the Texas Historical Commission. So after you make that right turn, and then I don't know, Doug, if this is correct, we still come in through this side gate, correct? Okay, you work your way around over here. This is the parade grounds. This is where we set up the scopes, usually down here. These were barrack ruins. I think the RVs are allowed back here, and then this is the barracks where people are allowed to sleep. Big flagpole, so I've got this one here just dialed in a little bit, just short of pixelating. Parade grounds are wide open. It's just a wonderful, beautiful place. I don't recall the Bortle rating, but it's going to be a heck of a lot better than Chris's, muck up city here in Houston. Connie and I at one point, many over 15 years ago, a while ago, we're actually able to see our shadows by the Milky Way. Views of the barracks and among the ruins, people set up their scopes. They're usually out here chatting during the day. They're not having their laser pointer fights yet. Scopes are usually covered, but people are around talking, checking out, getting things going. There's parking in the back of the barracks. There is RV row, but that used to be up next to the ruins, but not anymore. I think that's like another, 20 or 25 feet back. But there is water service and 30 amp service if you take an RV. Wander around, you usually find people have made too much food, so they're more than willing to share. This is a Friday night barbecue, which we can't do this time because there is a burn ban. So if you can do it electric, the way these guys are doing it in the walk, you're golden. Oh, they're doing it up at the maintenance shed, yeah. Yeah. You see this guy, Fred Miller, stay close. He tends to cook very well and cook a lot. And actually, I think he's on the list to go. So Fred's a great guy. Usually we try to gather for a mandatory picture, though I haven't seen one. Aerial view. This is actually, I think, taken by Connie. There's the ruins, cars. That's actually my old 4Runner. There's an aerial view of the place. Okay, double check the weather, whatever you use. In March, we have had weather in the 70s and 80s. In March of 03, we had down to 21 degrees. Yeah, before the wind chill factor. Froze your water in the coffee pot. Check the weather and plan accordingly. October can be nippy as well, too. Sleeping bags and clothes appropriate for the weather. Don't bring a fleece bag if it's going to be 30 degrees. You're not going to have a good time. Go for the Scout motto of be prepared. Come with Google Maps, as you know, so you know how to get around to Menard and Junction. I'll talk about those in a little bit. Fort will require you to sign a release of liability for you to be there. In other words, you're on your own and at your own risk. I think the request is to arrive anytime after 12 p.m. on Thursday. Bring food, cook, buy all your meals, plan on bringing a cooler with ice. Some people may make a run for ice to Menard or Junction. You can always coordinate that. Friday, excuse me. Friday night is a potluck meal, plan for alternatives. Given that's early enough on Thursday, a group usually heads to Menard for one of the local restaurants. The restaurant of the day is now Los Abuelos. I won't go into the details, but it's a fairly new restaurant that is apparently fairly accommodating and open when you actually get there. The other one has not. Ice for coolers, you've got two options, a Menard and Junction. I mentioned that. Hopefully word will get around if somebody's making an ice run. Plan on what to eat, how you want to work it. If you don't have a camp stove, bring a floating table and electric skillet because there will be power supplied. Don't forget the coffee pot. Bring plenty of bottled water and chapstick. You are 2,300 feet up and it does tend to get dry. Arrive Thursday, but not before noon. Friday, breakfast and lunch, you're on your own. Dinner's the communal potluck. Saturday, all 3 meals on Saturday are up to you. Some will go for an early dinner back to one of the towns or make it where they happen to be. Sunday, you're on your own, but you're also packing up to head out. Anyone needing to go has to contact Lisa Lester. She kind of coordinates the reservations on site. And I do encourage you to go. What you will find at Fort McCavitt, showers, they're 2 open air showers, they're enclosed. JSCS at one point funded the construction of those showers. Yeah, and Bob Taylor built it. Buzzards and airplanes with really good cameras could see you, so don't worry about it. You can actually see the stars by your shower. Bathrooms and porta potties, nice people, great skies, great weather, and it's a reason to get away from it all. So if you're tied to your phone, you're gonna have a problem. AT&T is passable, but Verizon usually goes DOA about 2 miles north of I-10. What you won't find at Fort McCavitt, quite a bit, but you need to be self-sufficient. What you're gonna find at Fort McCavitt is the sky. Nearest town is Menard, as I mentioned, 23 miles away. Junction's 40, but there's a lot more to it. Nearest Walmart, if you're a Walmart addict, is way out in Brady. That's 60 miles. San Angelo is 80 miles one way. So you're out there for a reason. If you get the feeling you're out there in the middle of nowhere, you're there for a reason. And the important thing is to have fun. So throw any questions you've got on the list, Doug, myself, anybody else in the club, and go ahead and contact Lisa Lester. All right.
Thank you, David. Okay, we got 3 minutes. Okay, Dave was just talking about Fort McCavitt X-Bar. There's still a cabin available at X-Bar if you want to go to X-Bar right after Fort McCavitt. Get on X-Bar webpage, you can get reservations. It's great. It'll be fun. We're doing that so we can have more nights under the sky. Okay, door prize. Look for your door prize number.